Okay, welcome to Wednesday. Um, Go ahead and get out your homework. Let's see. Today's the last lesson before the test. We'll review on Friday, test on Monday. All right, so I gave you 1 through 18 all. Questions 1 through 8 were your standard table where they had you fill in 2 particular values. So here we go. Number 1, the area is 196 pi and the volume is ugly, 1,372 pi over 3. Number 2, the area is 100 pi and the volume is 500 pi over 3. Number 3, the area is pi and the volume is pi over 6. Number 4, the area is 9k squared pi over 4 and the volume is 9k cubed pi over 16. Number 5, the radius is 4 and the volume is 256 pi over 3. Number 6, the radius is 9, the volume is 972 pi. Number 7, the area is 8 pi. Remember, area is surface area, total area. And the volume is 8 pi root 2 over 3. Number 8, the radius is 6. The area is 144 pi. All right. Number 9, trying to find. Okay, here we go. 2 answers. First one is 4, and the second one is 8. Number 10 was the same exercise, just with a different radius here. So the answers are 9 and 27. Number 11, 1 centimeters. You're finally throwing some units in here. Number 12, the area or the surface area is 36 pi meters squared. Number 13, it is 21 pi centimeters squared. Number 14, 15 pi centimeters squared. Number 15, so volume of a hemisphere, that means half of a sphere. So it's 4 times the volume of the sphere. And number 16, the answer is no. Number 17, okay, number 17 was challenging, only because it's real world units. They didn't say what to round it to, but it was 358 million 358 million square kilometers because we're doing surface area. All right, and then number 18 was 2 parts. Part A was 113 centimeters cubed, and our answer B was 103 centimeters cubed. There you go. All right, as I mentioned before, review on Friday, test on Monday. District 49 is going to call for a day of rest. In other words, no classes on that Monday on the 11th, and then we'll jump right into semester final review. We're just going to do 2 days of semester final review. That following week, we'll put forth, say on Monday, you'll see the semester final schedule, basically for 9th graders. 2 of the days you'll have 2 finals, and on 3 of the days you'll have 1 final, meaning that I believe Monday and Thursday, if that's right. No, maybe it's Tuesday, Thursday. Something like that. I'll put out the schedule next week. But 2 days you'll have 2 finals, and 3 days you'll only have 1 final, which is pretty convenient. On a normal, I mean, if we were back in the classroom, you'd anticipate every day you'd have 2 finals. But special. All right. Here's tonight's homework. You're going to like today. Today's a pretty easy day. All right, so the lesson is on areas and volumes of similar solids. And by areas, they mean surface area. So surface area and the volume of similar solids. There's only one theorem. Write this down, please. What is a similar solid? That's solids, and with solids we mean shapes. Shapes that have the same shape, just a different size. You've seen this before, right? We did this when we had similar figures. Remember, small triangle, big triangle, same shape, just different size. So here's the deal. The theorem expresses the relationship between 2 similar solids, their scale factor, their surface area, and their volume. In order to do that, once again, because we're going to be dealing with things like cones and cylinders and spheres, remember we didn't never really prove, excuse me, we never really proved those things to you. We just gave you the theorems and the formulas. And so, since we're still going to be talking about the same shapes, this is going to be a pretty weak. It's not a proof, right? It's just justification. So we're gonna go through a process that justifies where these formulas come from. So first thing we're going to do is we're going to gather some data. I'm going to give you two, or I'm going to claim that these are two similar shapes, right? I'll have a small one and a big one. And then we're just going to do some calculations with these particular shapes. So imagine we had two similar cylinders or two similar square pyramids, regular pyramids, right? Cylinders are also right, okay? So these are two separate problems, right? Cylinders and then pyramids. In example or figure one of each one, the larger shape is 1 and the smaller shape is 2. Okay. So I'll need you to pause the video and draw this table for me. Okay, you got the table done. So I mean, this is what the book is going to use as quote proof of the theorem. So this is just, you're going to recognize the patterns, and we'll reach some conclusions based upon the pattern. But this is certainly not strong proof of why it works. So we'll have to wait till calculus for that. All right, so we'll do one shape at a time. Notice the first column there says scale factor. Then it's got a ratio of the base. And then the next one is the ratio of the lateral area, in other words, the sides. And lastly, we got volume. Okay. And then, and then the middle column is for the cylinders, and the last column is for pyramids. So we'll do the cylinders first. Okay. So let's see. So we got the first thing we got to fill in is scale factor. Remember, scale factor, if two shapes are similar, the scale factor is simply corresponding parts of one written as a ratio. So for instance, if I wanted to go big to small, right, for my scale factor, let's see, I could either use the radius or I could use the height. Let's just, for sake of argument, let's use the height. So the height of the large one is 12, and the height of the small one is 8. You see where I'm getting those numbers from? Reduced, therefore the scale factor is 3 over 2. And notice that would have gotten the same value if we would have done the radius. 6 over 4 is 3 over 2. So the scale factor of the cylinders is 3 over 2. Okay? The next thing, we'll just go straight down that column there. It says we got to do the ratio of the base perimeter. So base perimeter, what does that mean for cylinder? That means the circumference, right? So the base of a cylinder is a circle. The perimeter of that circle would be its circumference. All right, what's the formula for circumference of a circle? 2 pi r, pi d, either one. All right, so let's see. And we're going to keep the same ratio. So we're going to do big to small. So let's see. 2 times pi, and the radius of the big one is 6. And the radius of the small one is 4. Do you see where I'm getting those numbers from? Reduce. The 2's and the pi's cancel. We're left with 6 over 4. In other words, it's the same ratio, 3 over 2. So it appears that if you have two similar shapes, in 3 dimension what we're talking about, solids, so two similar solids, that the ratio of the bases is the same as the scale factor. Okay. How about the lateral area? All right, so remember the formula for lateral area of a cylinder? That would be the sides of the circle, or the side, singular. Well, the side is curved surface, right, lateral surface. And remember when we made the net of this, when we cut it open, we found that it was a rectangle. And the rectangle, length times width. The width is obviously the height, and the length, right, would be the circumference of the circle. So 2 pi r h would be the formula for the lateral area. Okay. All right, so let's see. Once again, we're going to do big over small. So that would be 2 pi RH over 2 pi RH with the variables for each individual cylinder. So let's see, big to small, RH would be 6 times 12. And then the small one would be 4 times 8. You see where I'm getting those numbers from? Once again, let's do some canceling. Let's see, the 2 and the pi cancel, so 6 times 12 is 72, 4 times 8 is 32, which reduces to 9 over 4. Now I'll do a little bit of magic. We okay so far? Okay, 9 over 4. 9 can be written as 3 squared, and 4 can be written as 2 squared. You see where I wrote there? All right, so that's going to go there, and I think you can kind of see something going on there that's suspicious. Well, the scale factor and the ratio of the bases, the perimeter of the bases, was the same, and it looks like the sides, the lateral area of the similar shapes, is the scale factor squared. Okay? If that's truly what's going on here, then when we do it for the pyramids, we should get the same answer. Not 3 squared over 2 squared, but the scale factor squared. Okay? All right, how about volume? Anybody want to wager a guess? If the lateral area was big 1 squared over little 1 squared, what do you think the volume is going to be? Okay, that's a good guess. Let's see if you're correct. All right, what's the formula for volume of a cylinder? Someone, please. Thank you. Pi r squared h. Once again, you got to make sure you do the same comparison for each one, big over small. Now, it would work if we did small over big as well, too, but you'd have to carry that throughout all these examples. But we did big over small, so let's continue. Big over small. So pi, the radius is 6, and the height is 12. So pi 6 squared times 12 over pi 4 squared over 8. Times 8, sorry. All right, cancel. The pi's cancel. Ooh, big ugly number. Let's see. 6 squared is 36. 36 times 12 is a big number. 4 squared, 16. 16 times 8 is also another big number. When that fraction right there is reduced, 432 over 128. I'm not going to bother with showing you how I reduced it, but when we reduce it, we get that right there. Okay? 27 can be written as 3 to the third power, and 8 can be written as 2 to the third power. So, did we get what we expected? The answer is yes. Now, if this is truly a theorem, right, then when I do it for the pyramids, I should get the same answers. In other words, the lateral area and the base perimeter ratio should be the scale factor, and then the scale factor squared for the lateral area, and the volume should be the scale factor cubed. Let's see if that works. Okay? Once again, this is definitely not a proof. However, it is solid evidence that this is probably true. Let's see. All right, scale factor. Once again, we pick any distance, but we got to pick the same. And we're going to do large over small. So large over small. So it doesn't really matter which one you pick. I'll pick the slant height here. So let's see. The slant height of the large one is 10. The slant height of the small one is 5. 10 over 5. Hey, that's 2 over 1. And I'm not going to write 2. I'm going to leave it as 2 over 1. Notice that would work if we did it for the height and also for the side. Remember, this is a regular square pyramid. Okay, makes sense? All right, so 2 over 1. All right, the base perimeter, let's see. Perimeter, well, perimeter is the distance around, and since it's a square, well, one side is 12. 4 12s would be 48. That would be for the big. And for the small one, let's see, one side is 6. Can you see the 6? So 6 times 4 is 24. So we get 48 over 24, which once again, hey, we got the same number. Notice we didn't get 3 over 2, nor should we, but we did get the same ratio for scale factor and for the ratio of the perimeters of the base. Okay? All right, so that kind of confirmed. So if it's true, then when we do for lateral area, we should get what? Look at the pattern. Yeah, we should get 2 squared over 1 squared. Well, let's see if that works. So lateral area, if you remember, this is the hard one to remember, was the perimeter of the base times the slant height all over 2. Remember that? For lateral area, it was PL over 2, right? All right, so let's see. The perimeter of the large one, well, we just did that. That's 48. The slant height is 10, and we got to put that over 2. The perimeter of the small one is, what, 24? Times the slant height is 5, all over 2. That's an ugly fraction, but don't panic. All right, I'll do the numerator first. Let's see, 10 divided by 2 is 5. 5 times 48 is 240. The bottom one, notice I'm not going to divide 5 by 2, but I can do 24. 24 divided by 2 is, what, 12, and 12 times 5 is 60. So I get 240 over 60, which can be written as 4 over 1, which is, in fact, 2 squared over 1 squared. So we got what we expected. What should we get with the volume? Okay, I know we're waiting for this not to work, and trust me, it does work. All right, so yeah, we should expect that we should get 2 to the third power over 1 to the third power. All right, let's see if that works for volume. Who remembers formula for volume of a pyramid? Well, there was a couple of them. The one that I'm going to use is the base area times the height divided by 3. Remember that one? Okay. So let's see what works here. Base area. The base is a square. And then remember, capital B doesn't stand for the base, it stands for the base area. So let's see. For the large one, the base would be 12 times 12, 144 times not the slant height, but the height. So 144 time. Well, how about we write 12 squared to save ourselves some time? So 12 squared times the height is 8 all over 3. And the second one would be what? 6 squared times 4 over 3. All right. Okay. Well, we do that math. I'm going to jump to the answer here, but I'm sure you guys can handle this. 12 squared times 8 divided by 3 is 384. 6 squared times 4 divided by 3 is 48. That would reduce, all right, after you do some reducing, check my work, that would reduce to 8 over 1. And 8 over 1 is 2 to the third. And 1 obviously is 1 to the third as well, too. So we got what we expected. Okay? Makes sense? All right. We did a whole lot of work. What the heck did we just do? Here's what we did. We did what is called Theorem 12-11, which says this. You've got two similar solids, right? And they are in the ratio of A to B, right? The scale factors, right? Remember, scale factor, you pick any corresponding parts of two similar shapes, right? That gives you your scale factor. So if the scale factor of two similar solids is A to B, then you get three things, right? First off, the ratio of the perimeters is also A to B. That was the first thing we figured out, right? The second thing we found out that the lateral area, and we didn't do it for total area, but you could see that, the lateral area and total area is A squared to B squared. Now, notice, it doesn't have to be large to small. It could have been small to large, and it still would have been A squared to B squared. And then lastly, the volumes are A cubed to B cubed. Okay? Just want to point out in point 2, we didn't have a row there for total area, but we found out that the base area was correct and the lateral area was the same. Okay. All right. So how do we use this? Or go ahead and pause the video and make sure you write this down. So how do we use this? Well, they'll give you two similar shapes, right? Two similar solids, and they may only give. Okay. So all we did was one theorem. Hey, if only the rest of the book could have been this easy. So there's your homework. If you have any questions, make sure you email me. We'd love to give you some assistance on this because I'm bored. No, because I do have the time. If you're getting a little bit antsy about finals, don't be. I'll take care of you. I'm not saying I'm going to give you a pushover test, but I will certainly make sure that it's a passable test if you pay attention to the review. Okay. So with that, I'll close the class, and I will see you guys on Friday.